Hey everyone. In this video, we're going to talk about z-scores, which we've actually talked about previously in this course. And we actually used this data, the height of Czech male gymnast. We use z-scores to figure out how to find an outlier or to identify possible outliers in a data set. And the idea behind it is that a z-score is the number of standard deviations away from the mean any data point would be. So x in this case, x is a data point. Mu is the population mean. Sigma, which I think I figured out. Nope. Sigma is the standard deviation, is the population standard deviation. And so Z stands for z-score, or the standard score. So when we talk about standardizing data, what we're doing is we're taking two things that we normally couldn't compare, and we try to compare them. So the example I have here is we have the height of 50 male Czech gymnasts, and we have the height of 50 male NBA basketball players. Now, a Czech gymnast might think they're tall because they're taller than all the people that they always hang out with, which is other Czech male gymnasts. However, compared to an NBA basketball player, a Czech gymnast is really short. So we can't compare relative to the group that they hang out with the most, their heights. But we can standardize their heights. What we can do is we can say, hey, the tallest Czech gymnast, how does that compare to the tallest NBA player? So what we're going to do is, first, in order to find the standard deviation or the z-scores for the heights of these gymnasts, I need to know the mean and the standard deviation for the Czech gymnasts. I'm going to find that for the Czech gymnasts. I'm also going to find it for the NBA players. And what we're going to see is if I were to create a histogram for the Czech gymnasts, okay, you can see the numbers along the bottom here start at 63.1, they go up to 75.7, okay? If I do the same thing for the NBA players, and I'm sure I could change the number of bins here to make this a little bit nicer looking. Yeah, there we go. We can see both of these are pretty normally distributed. I mean, they are normally distributed. You can just see that the numbers along the bottom are the things that are different. So here we have, we're starting at 63.1 and ending at 75.7. Here we're starting at 70.8 and ending at 90.5 inches. Okay. And so I think, how many bins do we have here? Oops. So we have 6 bins here. Let's make 6 bins here and see if we can really make this a little bit better. All right. Let's make the bin width 4. Let's make the bin width 3. All right. So looking at these data, it's hard to compare. Like, is the 71-inch Czech gymnast tall? I mean, he's taller than most of the other Czech gymnasts. That would compare to someone who's like 86.4 inches here in this data set. So what we can do is we can turn both of these data sets into standardized scores. So we're going to turn them into z-scores. I'm going to find the mean. So the average of my Czech gymnasts is 68.8. I can copy this over. It's going to be blank. I can just change B to C here. And you can see the average NBA player is 79.046 inches. And then standard deviation, this is actually a sample. I know I used population mean and population standard deviation, but we're going to use the sample mean and then say, well, this is representative of the larger population. So we're going to find the standard deviation of both of these data sets. All right. So now we can find the standard score. So there's a couple ways we could do this. We could just use this formula here, which would be parentheses, the x value minus the mean. I'm going to lock the reference to the mean because that's going to stay constant, divided by the standard deviation, which I'm also going to lock the reference to. And you can see that this z-score is negative because this value is smaller than the mean. And I can copy these down for all of my gymnasts. Okay. The other way I could have done this is I could use a built-in formula, and that built-in formula is called standardize. And standardize, you use the value, you choose the value x, and then you choose the mean and you choose the standard deviation. Again, I would want to lock the reference to these two things because that's not going to change. And notice how we get the same value. I like to just create my own formula instead of using the standardized one because I can see exactly what's happening. But we have our z-scores. So now let's look at NBA players. I can find the z-score for this guy. This one should also be negative because this guy is shorter than the average NBA basketball player. So the larger the positive value of the z-score, the more standard deviations above the mean you are. So you can see that a 72.8-inch Czech gymnast is almost just as tall in his peer group. If you had them all lined up in a group, this gymnast at 72.8 inches would look really tall compared to all the rest of the gymnasts. The same amount of tall, basically, as this 87.6-inch NBA player. Okay, here's one that's really close. So you can see that someone who's 70.1 inches as a Czech gymnast would look just as tall compared to his peers as this 81.5-inch basketball player. Now this 81.5-inch basketball player is only slightly taller than the average. And this 72-inch, that's 6.5 feet, is significantly shorter than his peer group, and that would equate to someone who is 5'6". So that's a whole 6.5 inches shorter, but we're now comparing them to one another. So now if I were to graph a histogram of these data, you can see that the values along the bottom have shifted. And I'm going to change the bin width just so that the values are a little bit nicer to see or easier to see. So we're going to start with, we still can't really see these values. These decimal places are out too far. Typically, we round z-scores to 2 decimal places. which you can do here. Make this a little bit shorter. And then that automatically changes my histogram. Notice how right here in the middle, the tallest bar is where I transition from negative to positive, because 0 is always right in the middle of my standard normal curve is what this is called. And we'll talk about that more in just a second. So now let's graph the NBA players. And again, this is just a sample, so some of the values here didn't come out maybe the way we had hoped. I'm just gonna round to 2 decimal places. Okay, and you can see that this bar in the middle here, again, I think I can make this look a little bit better. There we go. This bar in the middle here is where we transition from negative values to positive values, because 0 is always right in the middle of my standard normal curve. So what we did was we standardized these, and now this is really apples for apples. If we have a 1.43 in this group, that would compare to a 1.43 in this group. And we could look, we could try to find here's a 1.42, and that's 72.1 inches. So a 1.42 z-score in this group is 72.1 inches, whereas a similar value, let's just go with the 1.47, would be 85.8 inches. Which brings me to our next example here. So this sort of gave us the reason why we need to standardize scores, and look at this is a great example of a standard normal curve. All right, the values along the bottom are called z-scores now. They're not heights. We stripped the heights away. These are just z-scores. They have no units. It's just how many standard deviations am I above the mean or am I below the mean? And since this is normally distributed, this follows the empirical rule. And we can use the ideas of normal distributions to answer questions about this. All right, we'll do the next example in the next video.